We can go to the next speaker, Anran Duan, and start sharing. And the title of the talk is Analyzing Wave Attenuation in the Antarctic sea ice using ship motion-derived wave spectra. Anran Duan, you can start sharing your screen. You are not audible. Can you unmute yourself? Anran.
Sorry?
Oh, yeah. Okay, now you are audible.
Yeah, okay.
Okay, you start presenting.
Yeah. Hi everyone. My name is Anran. I'm in my first year of PhD at the University of Melbourne, and my research focuses on wave attenuation in the marginalized zone of the Southern Ocean. And today I will give a presentation of my recent work on converting ship motion data measured during cruises in the Southern Ocean into wave spectra. Also, I will show a preliminary analysis of wave attenuation using this dataset. And to start with, I would like to give some introduction on the topic of wave attenuation within the marginalized zone. There are several previous studies of wave attenuation based on data collected from field observation, including both in-situ observations and remote sensing. The in-situ observations collected by buoys deployed on sea ice provide highly valuable information. However, there are limitations in terms of spatial coverage. The location of buoys are uncontrollable as they depend entirely on the movement of ice floes. The other observations method, remote sensing, relies on images captured by synthetic aperture radar about satellites. These images offer extensive coverage spanning across the marginalized zone. However, their limited resolution makes it challenging to distinguish shorter waves, and it is hard to separate wave features from ice features. There is a research gap in analyzing wave attenuation using both widely covered and high-resolution datasets. This present study aims to contribute on this by analyzing wave attenuation using ship motion measurements collected during cruises in Antarctica. Based on previous research and the datasets we have, this study aims to address two objectives. The first objective is to build an extensive database of waves in the Southern Ocean based on ship motion measurements. And secondly, we aim to investigate wave attenuation in the marginalized zone. We will also examine how this risk correlates with varying ice conditions. For the first objective of converting ship motion measurements into wave spectra, we utilize the method presented in this paper. In the following section, I will give a brief introduction to the principles of conversion. So, this study is primarily based on the 6 degree of freedom ship motion response, which is recorded by the onboard inertial measurement unit (IMU) during the cruise. In our analysis, we specifically utilize the ship's HIF data to reconstruct the full wave spectrum. The ship acts as a large buoy in the ocean, filtering out a portion of the wave energy, especially for relatively high-frequency waves. To convert ship motion to sea state, we first divide the time series of the ship's HIF motion response into 20-minute segments, using the HIF data in each segment to compute the measured response spectra. And then we reconstruct the wave energy that the ship filters out using the transfer function called the response amplitude operator. The rho is the ratio of a vessel's motion to the wave amplitude causing that motion, and is defined over a range of wave frequencies. We divide the measured response spectra by the corresponding rho values to get the wave spectrum. We can see that the low frequency part of the reconstructed wave spectrum is not modified a lot, as the rho value is close to 1. In contrast, there is a significant increase in the upper tail of the reconstructed wave spectrum after applying the rho. We filtered out frequencies higher than 1.5 radians per second in the wave spectrum, because the measurement of high-frequency waves tends to be less accurate and can introduce noise into the spectra. As shown before, the accuracy of rho is crucial for deriving reliable wave spectrum. However, its computation, which requires the ship's geometry, draft, and forward speed, involves many uncertainties, and the ship's drawing is not publicly available, and the actual draft is unknown. Therefore, we rely on the satellite altimeter data for calibrating the rho by comparing the significant wave height. The satellite altimeter data has been calibrated by Rebel and Yang in 2019, made it a reliable source for calibrating our measured spectrum. And to avoid inaccuracies arising from sea ice, we only compare the measurement in areas where latitudes are below 60 degrees south for calibration. Finally, we use a trial and error approach to compute the rho with different drafts until the difference of significant wave height of the reconstructed wave spectra and the satellite observations is minimized. Note that the draft value can be unrealistic due to uncertainties from other factors like ship speed and shape, and the removal of high-frequency wave components. And the second source of distortion to the measured wave spectrum, the wave spectrum detected by the ship, is the Doppler effect, a consequence of the ship's motion in relation to the ocean waves. To mitigate this effect, we correct each frequency from the encounter spectrum, which is the spectrum detected by the ship, to restore the correct wave frequency using this equation. V is the forward speed and the theta is the wave direction. Since the actual wave direction during the voyages was not measured, we rely on wave direction from Error 5 reanalysis dataset for correction. It is important to note that while the Doppler shift distorts the spectral shape, it doesn't affect the energy content. Therefore, we can derive the true wave spectrum by rescaling it to have the same energy as before the Doppler correction, as shown in this second equation. And there are several IMU datasets from different cruises available for generating wave spectra. The most comprehensive dataset was collected from the Macclesfield campaign, where the ship travels between Hobart and the Antarctic region, as shown in this figure. This voyage took place during the resupply season between 2017 and 2018. Additionally, we also have IMU data from other projects during the resupply season between 2018 and 2019, as well as winter 2022. In total, we have cruise data for nearly 1 year. Next, I will show the results we have till now. Here we present a comparison of the significant wave height from satellite and our calibrated measurements from 2 cruises. We distinguish the measurements from the marginalized zone and the open ocean based on the ice concentration from satellite data. We can see that the HS derived from the IMU data shows good agreement with satellite over the open ocean, where the satellite data is known to be reliable. We then validate our results by comparing the significant wave height with Area 5 reanalysis data over open ocean. It also shows good agreement with a root mean square error of 0.65 meters. And the next slide shows the comparison of peak wave period with those from Area 5. The y-axis represents peak period from Area 5, and the x-axis shows values derived from our measurements. The left figure represents period without correction, and the right figure shows corrections utilizing the mean wave direction from Area 5. We observe that the correction of the peak period reduced the root mean square error, improving from 3.8 seconds to 2.6 seconds. However, this period correction is only feasible over open ocean regions, as Area 5 wave direction is unavailable when CS concentration reaches 25%. Therefore, to improve this correction, we plan to utilize the mean wave direction derived from our IMU data, which is available throughout the cruise. This is a box plot correlating the significant wave height with ice concentration during the Marcos Field campaign. The plot illustrates a gradual reduction in average significant wave height as ice concentration increases. However, even at high ice concentrations like the 80% shown here, significant wave height could be relatively large. In the following section, I will utilize our dataset on waves in ice to examine the attenuation of waves as they propagated within the marginalized zone. This is a sketch illustrating the rotation of the ship as it moves into the marginalized zone. We calculate an average spectrum for each hour, and then we set the wave just outside the ice edge as the incident wave and consider the wave propagating forward for 6 hours, assuming wave stationary over this scale, and observe how the wave changes as it propagates into the marginalized zone. To illustrate, I will use data from the first cruise in the Marcos Field campaign as an example. This figure shows the trend in significant wave height and ice concentration as the ship enters the marginalized zone. The solid blue line represents HS from our measurement, and the dashed blue line shows the HS from Area 5. These two lines highly coincide until reaching around the 61.5 degrees south, which might be the location of ice edge, as the estimation from Area 5 tends to be inaccurate where ice concentration is higher. The two red lines represent ice concentration from satellite data, but from different products. They highly coincide where ice concentration is high, but could have a relatively large difference near the ice edge. Generally, there is a steep decline in HS as the ship enters the marginalized zone, and it remains at a lower value as the ship continues to move southward. We initially assumed that the actual ice edge is located at 62 degrees south, where we can observe a sharp decrease in HS and a relatively continuous distribution of ice from satellite data. We set the time at this location as over 0 and consider the wave propagating forward for 6 hours until reaching 62.5 degrees south. Within the time range, the ice concentration varies from a scattered condition to around 20%. And then, starting from the third hour, set the wave at this time as incident wave and consider the next 6 hours until the 9th hour, the ice concentration increased slightly up to around 25%. Finally, we consider the wave from the 6th hour to the 12th hour, during which the ice concentration increases significantly, varying from 20 to 40%. For each group of waves, we calculate the attenuation rate separately. Using this equation shown here, we can calculate the attenuation coefficient for each frequency component. In this equation, S0 is the incident wave spectrum measured at the SH, and S is the wave spectrum within the marginalized zone, and D is the distance between these two locations. Therefore, for each group of wave spectra, we obtain 6 sets of frequency-dependent attenuation coefficients. We calculated an average for each group of the coefficient and plotted them on a log-log scale against angular frequency separately. They are fitted with power trend lines, each with a different value of power n, starting from 1.07 for the 0 to 6 hours group, where the ice concentration varies from 0 to 20%. In the next 3 to 9 hour group of our wave, where ice concentration increased to up to 25%, the power value increased to 1.47. And in the last 6 to 12 hour group, where the ice concentration varied from 20 to 40%, the power becomes 3.76. This trend in the value of power indicates that as the ice concentration increases, the ice becomes more efficient in attenuating high-frequency waves. In subsequent analysis, incorporating power values from other voyages, we aim to discover the relationship between power values and ice concentration. Additionally, we plan to explore using two-terms monomials to fit the data to see the difference in the results. This analysis of wave attenuation is preliminary and will be refined in the future. In summary, we have successfully transformed the ship motion measurements from cruises into wave spectra and validated their accuracy against satellite and Anran 5 datasets. And then we conducted a preliminary analysis of frequency-dependent wave attenuation, investigating the relationship between ice condition and the power value n. In the next stage, we plan to improve the correction of wave periods affected by the Doppler effect by using a more reliable wave direction measurement, which will be derived from our IMU data. This same approach can then be applied to process the IMU data from other cruises. Once we have built the database of waves in the Southern Ocean, we can perform in-depth analysis of waving ice physics using this dataset. That's all of my presentation. Thanks for listening.
Thank you, Anran. We have a few minutes for question and answer. Any question from the audience? Yes, Professor Mellon, you have a question?
I have a question.
Yeah.
Sorry, this one mic was talking to another mic. On page 15. So how did you go from the on the left there, you've got the HS, and on the right, you've got wave spectrum. So how did you calculate those? It wasn't clear to me how you got the spectrum from the wave height from HS.
We actually get the HS from this wave spectrums. We calculated the HS from the wave spectrum.
How come the wave spectrum is so smooth then? When the if you smooth those wave spectrum, is it just, I would have expected it to be spikier if it was from a measurement. But those are measured wave spectra. Anyway, you've answered my question. The other thing is on page 17, that yellow line doesn't seem to fit the dots very well. Slope looks wrong.
Yeah, I will need to improve this.
And what was I don't understand by this 0 to 6 hour group. What does that mean?
So for this group, I mean, so for example, start from this location and consider the ship moves 6 hours forward and to this location, and we consider the wave stationary within this scale, and and analyze how the wave.
Okay, so they're different transects, but you wouldn't and you don't really, I mean, I'm wondering, is the ice concentration really so similar? Or do you think the ice concentration is changing a lot? Because the ship's moving and then 12 hours later, it's somewhere else. So, because I know you've got the ice concentration being almost the same.
Yeah, this ice concentration is from the satellite data, and that data is got one average value per day, so it might be different to the actual condition. So
something's changed though, hasn't it? Like it's not, I mean, it's not just because 12 hours have passed. Something must have changed because those are quite different curves, aren't they? Like one of they're dramatically different.
Yeah, the actual ice concentration might be quite different from the satellite data, but we don't have the information.
What about suppose a big storm was coming, so the ship's getting chased by these waves? I mean, how do you know? Could that be possible? Or, I mean, could the ship sailing, could it be in different waves after 12 hours than it was at the start?
Yes. So for the wave 12 hours later, we use the wave at this location as the incident wave. So
yeah. And it's less, right? Significantly less. Yeah, because it's very strange to me how different those curves look. But all right, thank you very much for your talk.
Thank you.
Thank you, Professor Nalan. Any more questions?
If I may just add a comment on Mike's question.
Yes.
Hi, everyone. The difference in the curve, despite the values, the average values that are in the right-hand plot, they are primarily related to a different ice concentration. Because the light blue is probably at an ice concentration maximum of 40%. I think that the average in this case is a bit misleading. So as the ship moves into the marginal ice zone, concentration increase and the exponent of the attenuation increases as well. That's my understanding from the result.
Yeah, that makes perfect sense to me. Yeah. Because it's gonna, and that ice product is terribly vague. Yeah, from the satellite.
Yes, because at the very beginning of our analysis, the ice is very much scattered. So there are patches of sea ice and patches of open water. Then for the yellow quadrant, she started to see a consistent increase of ice concentration. And then for the light blue quadrant, the ice is present substantially. Unfortunately, we don't have a photograph of the sea ice state in that condition, so we just rely on the concentration from the satellite. But there is definitely an increase of sea ice cover throughout the journey. This is why the slope of the line is changing.
Yeah, it's really interesting. I love the you know, and I love how much it varies. I mean, that's crazy. It's really interesting, quite consistently. Anyway, thanks very much.
Thank you.
Okay. So any more questions? If not, let's thank Anran for our presentation.